Hi, this is a quick video tutorial regarding image data and Python basics. Throughout these tutorials I'll be using the program Jupyter Notebook so that we can interact with code snippets and see what each piece does. Assuming Jupyter is already installed on your workstation, you can open Jupyter Notebook by opening a terminal window and typing Jupyter Notebook in lowercase letters, and this opens a file browser. From the file browser, select the notebook file to open. I have placed this tutorial notebook on the desktop. To run a cell, first select one, and then press Shift-Enter or the play button, which will run the cell, and proceed to select the next. To begin, we import the required open-source Python packages. NumPy is a package dealing with arrays of numbers. Matplotlib is a plotting library for data visualization. ImageIO deals with input and output, or reading and writing of images. CV2 is an abbreviation of OpenCV, which is a common image manipulation package in Python and other languages. First, we'll create a NumPy array that has a height and width of 3 by 3. The first column of the array is zeros, the middle column ones, and the third column zeros. We store this array in the variable image. We can view the stored data directly running this cell to print the stored data to the screen. We can view the array as an image, giving color to the array using Matplotlib's imshow function. For now we will view images using the gray color map because this two-dimensional array is a grayscale image and only has height and width, but no color channels. Notice because our values are only zeros and ones, 0 is black and 1 is white, as the columns we defined. We can look at the shape of the image and see the two dimensions are both 3 in size. Let's make a rectangle, adding a couple more columns to the array. We can view the shape of this image and see that it is 3 by 5. Importantly, we think of the x-axis as the horizontal and the y-axis as vertical as with traditional Cartesian coordinates, but here the y value is referenced first. So the dimensions of the rectangle are y, then x, and the rectangle is 3 by 5. Also notice that the array values are indexed starting from 0, and 0, 0 is the top left corner of the array, so the indices of the array values are 0, 0, 1, 0, 2, 0, and then 0, 1, 1, 1, etc. The y-axis indices increase moving downwards from the origin at the top left of the array, while the x-axis indices increase to the right. We can multiply the whole array by 255 and nothing changes in the image, but the data in the array itself, ones, are replaced with 255. The image is now on an 8-bit color scale, meaning each value can be 1 of 2 to the 8th or 256 possible values. Therefore numbers can be 0 to 255. We can also load in an image by defining an image file path to an image on the computer, and then read in this image as an array and similarly store it as the image variable. We can view this image and look at its shape. This is a transgenic zebrafish with neutrophils fluorescing in green. Notice the shape of the image is 3072 by 3072 by 3 because we have height and width which Matplotlib shows us on the two-dimensional plot, but then there are 3 image channels corresponding to red, green, and blue colors. Each of the 3 two-dimensional arrays is by itself gray, but when we stack them on top of each other and call them red, green, and blue, we get color. We can quickly compute the number of pixels by multiplying the first element of the image shape, the height, by the second element of the image shape, the width, by the number of color channels, which is 3, and we can print that value to the screen and format the value in scientific notation because maybe we want to see it that way. Let's next crop the image to see only the part of the image of interest, the fish. Here we take the image array and we select pixels 1200 to 2480 along the y-axis and 580 to 1220 along the x-axis and store this array subset in the variable cropped image, and then we view the cropped image and return its shape, which is now 1280 by 640 with 3 color channels. Maybe I want to rotate the image because I just want it to fill the screen more efficiently for better viewing, so we can use OpenCV's rotate function to rotate the cropped image array 90 degrees clockwise. The shape of the image has changed and the height is now 640 while the width is 1280. Maybe we want to make the image smaller, so we can take the rotated image array and select every 16th pixel in both the y and x dimensions and select all the color channels by inserting this colon in the third dimension. Notice on the screen the image stays about the same size when displayed, but the plot axis tells us there are many fewer pixels. The shape of the image is now 40 by 80 by 3, and we can see the resolution of the image has been reduced by a factor of 16, with the individual pixels appearing much bigger now. Here, we have decimated or binned the image by 16. These two words are used interchangeably, but we have selected every 16th pixel to downsample the image and make it smaller. What if we want to make it bigger again? We can take the height and width of the small image, multiply them by 16 and define these as the new height and width, and we can use OpenCV's resize function to resize the smaller image to the new width and new height, which are really the original height and width of the image. Notice the shape of the image is back to the original, but the resolution of the image is still very low because we lost most of the array's data when downsampling. When we take the smaller image array and expand it back to the original size, OpenCV interpolates between the values it has to fill in the missing values, leaving us with the larger image, but still at very low resolution. So let's go back to using the rotated image, which was the original essentially because it's prettier at high resolution. This time I displayed it larger on the screen by telling Matplotlib I want the figure to be this size, but the array shape has not changed, it is only displayed larger. So to view the color component, we can select just the red color channel. We select all of the height and width, but only the 0-indexed color channel to get just the red pixels, and we view this again with the gray color map. The shape of the array only has the height and width dimensions again, and it is hard to see because there is not very much red pixel data in the green image. If we select just the green channel, we have most of the color data in the image and we can view it in gray easily. We can view the distribution of pixel intensity values by making a histogram from the gray image. We define that there are 256 bins and define our x-axis values here, which is just integer values from 0 to 256, but not including 256, so 0 through 255, and then we can plot a bar chart of the x and y data where x is our pixel intensity values and the y values are the number of each value that are present in the one color channel array. We see that the majority of the pixel values are almost 0 as they are very close to black, while there are many fewer values extending up to 255. Finally, we can threshold our image. So first we'll make a copy of the rotated gray image array and store it in the value threshold image because we are going to modify the array, but we probably don't want to modify the original. We'll take this copy, and any values that are less than 80 we set to 0, black, and now when we compare the gray image to the threshold image, we see only the brighter values of the array. Overall, this information is fairly basic but is critical to understanding how to work with image data on computers. In further tutorials, we will build off of these concepts exploring what the MCAM can do. Thanks for listening and I hope you learned something.